Hello everyone. In the last lecture I have explained the design steps of design of bearing bolted joint, and in this lecture we will solve a design problem. Okay, so let us solve the problem. So the question says two steel plates of 10 mm and 12 mm thick are to be joined by a lap joint so as to transmit a load of 120 kN using 20 mm dia bearing bolts of property class 4.6 and plates of grade Fe14. Then find the numbers and arrangement of bolts if each plates are 100 mm wide. Okay. So in the question it is clear that we have to design the lap joint. Okay. So it is given in the question that we have to design the lap joint, and I have already told that in case of design problem, the load that to be transmitted by the joint and the thickness of plate, these data will be given in the question. Okay. So here you can see the load that to be transmitted by the joint is given in the question, and also the thickness of plates, that is 10 mm and 12 mm. These are the thickness of two main plates. This is also given in the question. Okay. So given data are the load that to be transmitted by the joint is given, that is 120 kN, and the thickness of plates are also given in the question. So one thickness is 10 mm and another thickness is 12 mm. Okay. Then the bolt diameter is given. Okay. So I have discussed that if the bolt diameter is not given in the question, then we can determine the diameter of bolt from the Unwin's formula. So as here the diameter of bolt is given in the question, so there is no need to determine the diameter of bolt from the Unwin's formula. Okay. So we can take the diameter which is given in the question only. So the diameter of bolt is given, that is 20 mm. Then next is the property class of bolt is 4.6. So from the property class of bolt we can get the value of the ultimate tensile strength of bolt. Okay, that is 400 MPa. Okay, because here 4 stands for 1 by 100 into ultimate tensile strength of bolt. So the ultimate tensile strength of bolt is 4 into 100, that is 400 MPa. Okay. So here FUB is 400 MPa, and the plate, the ultimate tensile strength of plate is also given. Okay. So FU is 410 MPa. Okay. Then it is asked to find the number of bolts and to arrange the bolts if each plates are 100 mm wide, and the width of the plate is also given, that is 100 mm. Okay. So we have to design the lap joint and to take this amount of load. Okay, and to transmit this amount of load, what should be the number of bolts required, that we will calculate. Okay. So in the first step we will determine the diameter of bolt. Okay. So the first step was to determine the diameter of bolt, but as here in the question the diameter of bolt is given, so there is no need to determine the diameter of bolt from the Unwin's formula. Okay. So as the diameter of bolt is given, so we can take the diameter of bolt as 20 mm, which is given in the question only. Okay. So, here the diameter of bolt is 20 mm. Then in the second step, we will calculate the strength of bolt. Okay. In the second step, we will calculate the strength of bolt. Okay, so to get the value of design strength of bolt, we have to calculate the shear capacity of bolt and bearing capacity of bolt. So, first calculate the design shear capacity of bolt. Okay. So, the design shear capacity of bolt is calculated by nominal shear capacity of bolt divided by factor of safety for the bolt. Okay. This gamma MB value is 1.25, that you can get from the table number 5. Then calculate the nominal shear capacity of bolt. So, the nominal shear capacity of bolt can be calculated by FUB by root 3 NN ANB plus NS ASB. Okay. So, here the FUB value is 400 MPa, that we got from the property class of bolt, that is 4.6. Okay. So, here the ultimate tensile strength of the bolt, that is FUB, is 400 MPa. Then next come to NN/NS, as it is lap joint. Okay, as we are going to design the lap joint, and in case of lap joint, only one plane is undergoing shear. Okay, lap joint is the case of the single shear condition. Okay, so in that only one plane is undergoing shear, and that plane generally at the threaded part. So, for the lap joint and for the single shear condition, NN is 1 and NS is 0. So, here put NN as 1 and NS as 0. Okay. Then next come to ANB. ANB is the net area of the bolt. Okay. And that can be calculated by 0.78 into pi by 4 into d square. So, here FUB is 400 MPa root 3, then NN is 1, ANB is 0.78 into pi by 4 into d square. Here the diameter of bolt is given, that is 20 mm. Okay, plus 0. As NS is 0, so this whole term is 0. Okay. So, the nominal shear capacity of bolt, this value is coming 56575 Newton. Okay. And you can write this value in kilonewton also, that is 56.575 kilonewton, as 1 Newton is equal to 10 to the power minus 3 kilonewton. Okay. So, this is the value of the nominal shear capacity of bolt, and this value we have calculated for one bolt only. Okay. For one bolt, the nominal shear capacity of bolt is 56.575 kilonewton. Then calculate the design shear capacity of bolt. So, here nominal shear capacity of bolt that we have calculated, that is 56.575 kilonewton divided by gamma MB, that is 1.25, and this value is coming 28 point something, that is 45.26 kilonewton. Okay. So, we have calculated the design shear capacity for one bolt is 45.26 kilonewton. Okay. Then next calculate the bearing capacity of the bolt. So next we will calculate the design bearing capacity of bolt. Okay. So the design bearing capacity of bolt that can be calculated by nominal bearing capacity of bolt and partial factor of safety for the bolt, and this value is 1.25, and this value you can get from table number 5. Then next calculate the nominal bearing capacity of bolt. So the nominal bearing capacity of bolt can be calculated by 2.5 into kb into d into t into fu. Okay. So here d is the diameter of bolt that is given in the question, that value, that is 20 mm. Then next is t. Okay. So as this is lap joint, so to take the value of t, we will compare the thickness of the main plates only. Okay. So here two main plates are there, and the thickness of one plate is 10 mm and the thickness of another plate is 12 mm, and we will take the minimum value. So here we will take the t as 10 mm, as the 10 mm is the minimum value between these two values. Okay. The next is fu. Fu is the ultimate tensile strength of the material or plate, and that is given in the question also. So that value is 410 MPa. Then next come to kb. Okay. So the kb is calculated by E by 3d naught, P by 3d naught minus 0.25, then fu b by fu, then 1. Okay. So here d naught is the diameter of bolt. Okay. So d naught is the diameter of bolt, diameter of bolt hole. Okay. D naught is the diameter of bolt hole that can be calculated by the bolt diameter plus clearance value. So the bolt diameter is given, that is 20 mm plus clearance value. So the clearance value you can get from the table number 19. So for 20 mm diameter of bolt, the clearance value is 2 mm. So here the bolt hole dia is 22 mm. Okay. So here take d naught as 22 mm. Then next FUB is for 400 MPa, FU is 410 MPa. Then next come to end distance and pitch distance. Okay. So these two value is not given in the question, so we have to assume these two values. So the minimum, so to assume these two value, first calculate the minimum end distance and minimum pitch distance. Okay. So minimum end distance is calculated by 1.7 d naught or 1.5 d naught. Okay. So I am taking 1.7 into d naught. Okay. So these codal provisions you can refer the respective clause numbers. Okay, that I have discussed in previous lectures. Okay, you can check. Then here 1.7 into d naught is 22 mm, and this value is coming 37.4 mm. Okay, so the minimum end distance is coming 37.4 mm. So we will take the value that is greater than from the 37.4 mm. Let I am taking the end distance for the design 40 mm. Okay, always we will take the greater value. from the minimum value. Okay. So I am taking the minimum end distance 40 mm. Then next calculate the minimum pitch distance. So the minimum pitch distance can be calculated by 2.5 into diameter of bolt. 2.5 diameter bolt is 20 mm and this is coming 50 mm. Okay. Let I am taking the pitch distance for the design 60 mm. Okay. So put the value of end distance and pitch distance here. So end distance that I am taking is 40 mm divided by 3 into D naught, that is 22 mm. Then next P I am taking, that is 60 mm. 60 divided by 3 into 22 minus 0.25. Then FUB by FU. FUB is 400, FU is 410, then 1. Okay. So this value is coming 0.606, 0.66, 0.976 and this value is 1. Okay. So the first value is 0.606, then 0.66, then 0.976, then 1. So we will take the minimum value for kb. So among these values 0.606 is the minimum value. So take kb as 0.606. So here we are taking the end distance as 40 mm and pitch distance as 60 mm. Okay. So put the values here. 2.5 kb value is 0.606, then diameter bolt, this value is 20 mm. Then thickness of plate, we will take the thickness of the thinner plate, so 10 mm, then 410. Okay. So the nominal bearing capacity of bolt, so this value is coming 124.225 Newton, and you can write this value in kilonewton also, 124.225 kilonewton. Okay. So then next calculate the design bearing capacity of bolt. So the nominal bearing capacity of bolt that we have calculated is 124.225 kilonewton. Then the partial factor of safety for the bolt, that value is 1.25 and this value is coming 99.38 kilonewton. Okay. So the design bearing capacity of bolt, that value we have calculated, that is 99.38 kilonewton. That also we have calculated for one bolt only. Okay. So next is, the design strength of bolt. Okay. So to get the value of design strength of bolt, we have calculated the design shear capacity of bolt and design bearing capacity of bolt. So next the design strength of bolt will be the minimum of design shear capacity of bolt. That value we have calculated is 45.26 kilonewton. Then the design bearing capacity of bolt, that is 99.38 38 kilonewton. So here the strength of design strength of 1 volt is the minimum of VDSB and VDPP. Okay, so the value is the value is 45.26 kilonewton. Okay. So the strength of bolt is 45.26 kilonewton. So here the second step is over, then come to third step. So in the third step, calculate the number of bolts required. Okay, so number of bolts required can be calculated by the force that to be transmitted by the joint, and that value is given in the question, that is 120 kilonewton, and divided by the strength of 1 bolt. Okay, so the strength of 1 bolt that we have calculated, that value is 45.26 kilonewton. Okay, so this value is coming 2.65. Okay, so we can round off this value to 3. Okay, so the number of bolts required is 3. Okay, so 3 number of bolts required to transfer the load, that is 120 kilonewton, from one member to another member. Okay, so the number of bolts required that we have calculated is 3. Then in the fourth step, just arrange the bolts in a convenient way. So in the fourth step, we will arrange the bolts. Okay, so this is the elevation of the lap joint. So let us draw the plan view of the lap joint. Okay, and the width of the plate is given also in the question, that is 100 mm. So here the width of the plate is 100 mm. Then next arrange the 3 number of bolts. Okay, so if we will arrange the bolts, we will arrange the 3 number of bolts like this way, then you can see here we have taken the end distance as 40 mm and we have taken the pitch distance as 60 mm. Okay, so we can, I have already told that we can take the edge distance, we can take the pitch distance and gauge distance same. Okay, so here we have taken the pitch distance as 60 mm, so take the gauge distance also 60 mm. Okay, so here the distance is 60 mm, here also the gauge distance is 60 mm, and the end distance is we have taken, that is 40 mm, and here also 40 mm. Okay, so here you can see that the width of plate becomes 40 plus 60 plus 60 plus 40, that is 200 mm. Okay, 200 mm, but our width of plate is given in the question, that is 100 mm. Okay, so we can't arrange the 3 number bolts like this way, as our width is restricted. Okay, as our width is restricted. So we can arrange the bolts in one row also. Okay, so here arrange the bolts in one row. Okay, so take the end distance as 40 mm, here also the end distance as 40 mm and the pitch distance as 60 mm, and here also the pitch distance is 60 mm. So as our width is restricted to 100 mm, so we can provide the 3 number of bolts in one column. Okay, so for that we have provided the 3 number of bolts in one row. Okay, so you can provide the bolts like this way. So here in the elevation these 3 bolts will be seen. Okay, okay, so we have arranged the bolts in one row, and in the elevation you can see the these 3 number of bolts, and this is the plan view of the lap joint. Okay, so after arranging the bolts, in the 5th step, just check whether the strength of joint is coming greater from this load or not. Okay, so first calculate the strength of joint, and to get the value of the strength of joint we have to calculate the strength of bolt and the rupture strength of plate, and the strength of strength of bolt that we have already calculated in the step number 2. So next calculate the rupture strength of the plate. So the rupture strength of the plate can be calculated by 0.9 into An into Fu divided by gamma ml. Okay, so here Fu is 410 MPa, then gamma ml is the partial factor of safety for the failure at ultimate stress, and this value is 1.25, and this value you can get from the table number 5. Then next is the net effective area. Okay, so here calculate the net effective area. So that can be calculated by B minus N D naught whole into T. Okay, so B is the width of the plate, and that is given 100 mm. Okay, then minus N. N is the number of bolt in the critical section. So here you can see 3 line of bolts are there. Okay, 3 line of bolts are there, and in case of chain bolted case we always take one section only. Okay, so I am taking this section. Okay, so in this line of bolt only one bolt is present, so take N as 1. Then next is D naught. D naught is the 20 mm. Then the thickness of the plate, so we will take the thickness of the thinner plate. So the thinner plate is 10 mm. Okay, so take the T as 10 mm. Then the net effective area, this value is coming 780 mm square. Okay, then put all the values in the formula. So 0.9 An, that value has come 780 mm square, then Fu 410, then gamma ml, that value is 1.25, and this is coming 230.26. 230.26, and here you can see this value, this rupture strength of plate, this value is coming greater than that of the load that to be transmitted by the joint, and that value is given in the question already. Okay, so this value is greater than 120 kilonewton. Okay, so our rupture strength of plate is greater than than that of the external applied load, that is 120 kilonewton. Okay. So, in this case our plate can easily transfer this amount of load from one member to another member. Okay. So, safe. Next, check for the strength of the joint. Okay. Check for the strength of the joint. So, the strength of the joint is the minimum of design strength of joint is minimum of design strength of bolt So, we have calculated the design strength of bolt for one bolt only, but the number of bolts required are 3. So, the design strength of bolt will be 45.26 into 3. Okay. So, this 45.26 is the design strength of one bolt only, but we designed that 3 number of bolts are required. So, the design strength of bolt at the joint will be 45.26 into 3, and this value may come 135 point something. Okay. And next is the rupture strength of plate. That value has come to 36 point something. Okay. So, here you can see that the design strength of the joint will be minimum of these two values. So, the design strength of the joint will be 135 kilonewton. Okay. And this 135 kilonewton is greater than that of the 120 kilonewton. Okay. So, we are on safer joint. Okay. As our design strength of the joint value is coming greater than that of the external applied load. Okay. So, our design is okay. So, in this way you can design the lap joint also and board joint also. Okay. So, here we have finished the theory part, the numerical part of the bearing bolted joint. In the next lecture, we will discuss about the analysis of the high strength friction grip bolt. Okay, thank you.